This question is from GATE 2014 Mechanical Engineering paper set 4, question number 35. A bolt of major diameter 12 mm is required to clamp two steel plates. Cross-sectional area of the threaded portion of the bolt is 84.3 mm square. The length of the threaded portion in grip is 30 mm, while the length of the unthreaded portion in grip is 8 mm. Young's modulus of material is 200 gigapascal. The effective stiffness in meganewton per meter of the bolt in the clamped zone is dash. Let's understand this situation better by a diagram and also note the given things there. So if these are the two plates to be clamped by using this bolt, we have this bolt going across it like this. Thickness of the plates is not given and it's not required also. Now, the threaded portion has a grip of 30 mm while unthreaded has a grip of 8 mm. So we'll assume that this much portion of the bolt is threaded. There are threads carved on it and this much is unthreaded. So we can note down the lengths of these portions as 8 mm and 30 mm. Dimensions are in millimeter here. Also, the bolt major diameter is given 12 mm. Now the unthreaded portion will have a diameter of 12 mm, but the threaded portion won't have a uniform diameter of 12 mm. And that is the reason why they have given the cross-sectional area of the threaded portion. While for the unthreaded one, we can calculate the cross-section area. So we'll write the threaded portion cross-sectional area 80 is 84.3 millimeter square. This is given. While cross-sectional area of the unthreaded portion, let that be AUT. We can calculate it by pi by 4 into 12 square because we know that there is a uniform diameter for the unthreaded portion which is 12 millimeter. Young's modulus is given 200 gigapascal. As we have to calculate the effective stiffness in meganewton per meter, we'll calculate this also in megapascal. So it is 200 meganewton per meter. Now let's solve this further. As we see, the two parts of the bolt are in series combination. So their deflections will be added up. We can write delta T plus delta UT, where T stands for the threaded part, UT stands for the unthreaded part. Deflection can be written as force per unit stiffness. So force applied to the bolt is going to be a single value. The tensile force that the bolt is subjected to will be same for both the parts. So let that be capital F divided by stiffness of the bolt. Let this be capital K will be equal to delta T will be simply force applicable to the threaded part divided by stiffness of the threaded part plus force applicable to the unthreaded part divided by the stiffness of the unthreaded part. We can take F common from here and cancel it out from both sides. So we have 1 by K is equal to 1 by small kt plus 1 by small k ut. This is nothing but the formula for calculating equivalent stiffness when these two parts of the bolt are in series and have different cross sections and different lengths. So let's calculate KT, KUT and then K. KT will be, bolt is a tension member, that is an axial member. So stiffness for axial member is simply given as its cross section area AT into Young's modulus E divided by its length LT, which will be equal to AT is 84.3 millimeter square into E is 200 megapascal. This is in millimeter square. E is in megapascal and megapascal is equivalent to Newton per millimeter square. There was a mistake here. This is 200 into 10 to the power 3. So we have to multiply with the factor 1000 in order to convert giga to megapascal. So we can substitute this as it is 200 into 10 to the power 3 Newton per millimeter square divided by length is also in millimeter. So for threaded portion length is 30 millimeter. When this is calculated in digital calculator, we get the answer as 562000 Newton per millimeter. Stiffness is in Newton per millimeter. Let's calculate KUT. KUT will be similarly AUT into E by LUT. Area of cross section is pi by 4 into 12 square. It turns out to be 113.097 into Again, E remains same, 200 into 10 to the power 3 because material used is same. So Young's modulus will not be different, divided by the length in millimeter, that is 8 millimeter. This turns out to be 2827425 Newton per millimeter. Let's now find out capital K. So capital K will be 1 divided by 1 upon KT plus 1 upon KUT. After substitution and calculation in the digital calculator, we get value of K as approximately equal to 468,900 Newton per millimeter. Now the answer has to be written in meganewton per meter. So let's convert this. In order to convert Newton to meganewton, we'll have to multiply with 10 to the power minus 6. And then to convert millimeter to meter, we'll have to divide with 10 to the power minus 3. So ultimately we have to multiply with 10 to the power minus 3, which will be equal to, that is dividing by 1000, we get this as 468.9 meganewton per meter. Let's go back and fill in the answer. So the answer is, effective stiffness of the bolt in clamped zone is 468.9 meganewton per meter. To learn more about bolted connections, you can refer to the NPTEL video Lecture 5 Introduction to Bolt Connections from the course Design of Steel Structures. This course is by Professor Damodar Maiti. He is from Department of Civil Engineering of IIT Kharagpur. I hope this solution will help you clear your doubt. Thank you.